Welcome to the second lecture on an introduction to large deviations. And the goal of this section of this lecture is to formulate and later prove the Kramer theorem. It is the generalization of the previous result, which we formulated last time, and also we discussed the proof of that result. Before, let me recall that the last time we proved the following theorem. 1.7 now it is in the script. And here we assume that we have a family of independent, identically distributed random variables, Xi, be independent, identically distributed, maybe shorter it is IID, random variables, such that the probability that Xi is equal to 1 is P, and probability that Xi is equal to 0 is 1 minus P. Actually, Xi have Bernoulli distribution with parameter P from 0, 1. And last time we showed that the sum of these random variables satisfies the following property. For every x larger or equal than p, that is the expectation of C1, we have that limit n goes to infinity, 1 over n logarithm the probability that Sn divided by n is larger or equal than x is equal to minus I of x. Well, this function, we know the form of that function. It is x logarithm x divided by p plus 1 minus x logarithm 1 minus x divided by 1 minus p and plus infinity. Here, if x is from 0, 1, and here otherwise. And now we want to understand what we have in the general case. How generally we can compute, we can define the form of this function, probably without going like trying to prove or obtain this kind of the limit for every family of independent random variables. And to give you the idea how we can obtain this function when the distribution of Xi is given, I would like to start with the following simple computations, which we will do in the first section of our lecture. We will call that section, first of all, it's to Kramer theorem. And the second is cumulant generating function. Function. I'm sorry. Then let's consider, as before, a family of independent, identically distributed random variables, but now not necessarily Bernoulli distributed. Let Xi1, Xi2, and so on be IID with expectation, for instance, psi1 is denoted by mu. Expectation exists and it is mu from R. And as before, consider Sn, it is the sum. And then we are interested how we can estimate the limit n going to infinity 1 over n logarithm the probability that Sn divided by n is larger or equal than x, where x is larger or equal than mu. It is like before, last time, we considered two cases. One case when x was larger than expectation, and another it was smaller than the expectation, and you have to consider that separately. We do the same here. By the way, here the limit cannot exist. Let me work with upper limit or lower limit. And now I would like to get the bound from above. The bound from above is much easier to obtain in general case than the bound from below. I will consider the lim sup. And then let's compute further. It is lim and goes to infinity 1 over n logarithm the probability that Sn is larger or equal than nx. And now here the idea is that let's consider the exponential moments, or like consider the exponent of the object that you want to estimate. I want to rewrite this probability inside, the event inside the probability as follows. I just take exponent larger or equal. I will put nx, I will put Sn, and of course I can take also some positive constant. And here we assume that the lambda here is larger than 0. And now having the probability, we can use the Chebyshev or Markov inequality to estimate the probability via the expectation. We estimate that as it is less or equal than limit and goes to infinity 1 over n logarithm and then expectation, but you will have 1 over e to the power lambda n x, and then the expectation of e lambda Sn. Note that here we do not assume that the expectation exists. It can happen that it is plus infinity, but anyway, the estimate here make always sense. Even the expectation is plus infinity. And now we can compute the expectation. First of all, we can separate that we can consider. So you see here the product of two numbers, and you have logarithm. Therefore, you can rewrite the logarithm as a sum. So let me do that. I will just take this part. I don't want to, or maybe I can continue. Okay, let's continue. It is lim n goes to infinity 1 over n, and you will have logarithm minus logarithm e to the power lambda n x, and then plus logarithm, and then the expectation, but you have exponent lambda of the sum of random variables. And now you can use the independence of the random variables psi I, because you have the expectation of the sum. Therefore, you can write the expectation as the product of expectations, and then you have expectation of product. And because of independence, you will get the product of expectations. You get, I'm sorry, I put here less or equal. It is actually equal. 1 over n. That can be in brackets, can be the first term in the bracket can be precisely computed. And the second term can be written as a product of expectation of e to the power c lambda I. Let's note that random variables are identically distributed. Therefore, this expectation, it is the expectation of only one random variable, say xi1. And then the product you will have like the power n, and then you can move that power n outside the logarithm. You obtain limit n goes to infinity 1 over n plus n logarithm e to the power e lambda xi. And now you see that here everything that you can precisely compute the limit here, because you have n here, which will be divided by this n, and you have n here. Then the result, the limit, is equal to minus lambda x plus logarithm expectation of e lambda xi. Let me denote this function here. The function depends on phi, or on lambda, I'm sorry. Oh, thus it is minus lambda x plus phi of lambda. And this is true for every lambda that is positive. Now, as an exercise, I propose you to prove that this expression here, it is that expression is larger or equal than 0 for lambda which is negative or 0. So let me write that. One can show that minus lambda x plus n is larger or equal than x is less or equal than minus lambda x plus phi of lambda. We got that for lambda positive, but taking into account that this expression here is positive, you see that for negative lambda or 0, you will have that this term is non-negative. But in this part, the probability is between 0 and 1. Therefore, the logarithm is non-positive, and the limit cannot be a positive number. Then the inequality here is automatically true for every lambda, also for lambda negative. And therefore, this request here, we can remove. We can write that lambda for every lambda from R. And now you see this strange parameter lambda that doesn't exist in the left-hand side, but it is in the right-hand side. And what is then the best estimate? Of course, the best estimate is if you take the infimum over all lambda. Since the inequality is true for every lambda, it is also true for infimum over lambda. You get lim n goes to infinity 1 over n logarithm the probability Sn divided by n larger or equal than x is less or equal. And I can write the infimum over all lambda of the right-hand side, but I want to put minus outside. And when I put minus outside the infimum I have to replace by supreme. To save our time, we will write just supreme. Minus supremum lambda from R, lambda x minus phi of lambda. Well, phi of lambda is, from the previous slide, it is logarithm e to the power lambda xi1. Okay, we got the estimate from above, and now our goal will be to show also that you will have the same estimate from below. So that lim info can be estimated from below also by minus supremum of lambda x minus phi of x, phi of lambda. But to prove the lower bound, it is much more complicated. And to be able to do that, first we need to understand the property of this function phi a little bit. Also, we need to discuss about that this supremum, try to understand some properties, and then using some properties of the right-hand side here, we will be able to obtain the estimate from below. Okay, when you want to work with some concrete, with some specific object, it is always useful to give some name for it. And we will do it here as well. Definition. In the lecture notes on my webpage, it is definition 2.1. Let Xi be a random variable on R. Then the function phi of lambda that is equal to logarithm expectation of e to the lambda xi for lambda from R, where the infinite value also is allowed for the expectation, and therefore for logarithm of, we assume that logarithm of infinity is infinity, is called logarithmic moment generating function. Generating function. Or cumulant generating function. Or generate. And just since we make some definition, we introduce the function which naturally appeared from our estimates. Let's try also to consider some examples. And since later we want to compare or we want to test everything using our example from the previous lecture, it makes sense to see how looks the cumulant generating function for Bernoulli distributed random variables. Because later we will show that exactly the function here, it will be the function I, which we found in the previous lecture. Just to show some consistent with the result that was obtained before. It is example 2.2. We assume that Xi has Bernoulli distribution. Xi has Bernoulli distribution with parameter P. And also let's choose this P is equal to 1 over 2. That means that random variable takes two values, 1 and 0, with the same probability 1 over 2. And then you see that just taken that this function phi lambda, it is, as before, logarithm of expectation e lambda xi. And now we need to compute expectation, and probably here I don't need to pay so much attention how to compute expectation, but maybe for some of you, I just say that here we just go through all values of discrete random variable, and then we take the value of this random variable and multiply on the corresponding probability that this value is taken. It is logarithm, and then you have two values, one, then you have e lambda multiplied by 1, 1 over 2, plus e lambda multiplied by 0, or 1 over 2. It gives you logarithm 1 over 2 e lambda plus 1 over 2. And using that, you can move 1 over 2 outside the logarithm using the property that logarithm of product is sum of logarithms. You will obtain minus logarithm 2, or logarithm 1 over 2, or minus logarithm 2, plus logarithm e lambda plus 1. Lambda larger, lambda from R. It is the cumulant generating function for this concrete case. And of course, now also it's clear how to compute, how you can find that function for any given distribution. You just need to take the expectation, compute the expectation, and you will get the cumulant generating function. One of the property of cumulant generating function is its convexity. Its convexity. This function is convex. Let me consider this as an exercise to form. It shows that the function p is convex. This I leave for you here. Only I will write hint. Use the Hölder inequality. And of course, definition of convexity to see that. Okay, good. Then we have that we introduced the cumulant generating function, but it was not our final goal. Our final goal to understanding what we have in the right-hand side of the estimate, it was the supremum of this expression. And this supremum, or we also can say transformation, because you have you have a function which depends on lambda phi. Then you consider this difference, and you take supremum over lambda, but you see that this part here depends on x. So therefore, you get some function on x. And this transformation of one function depending on lambda to function that depends on x, it has a name. It is a famous transformation, and it is used a lot, for instance, in the convex analysis. And the transformation is called Fenhill-Legendre transform. Then the next section of this lecture is Fenhill-Legendre transform. Okay, we need definition. Assume that we have some function f, which takes the values from r to minus infinity plus infinity, but including, because you remember that for cumulant generating function, we allow plus infinity. And this function is convex, B convex. Then the function f star of y that is given by supremum of x from r here I changed that the notation a little bit. But I hope that it's clear what we do here. As before, we have some function. Now we call that function by f. Here we write that linear function minus the given function, the linear function with some fixed slope, y, and then we take supremum. And this is called the Fenhill-Legendre transform of f. Is called the Fenhill-Legendre of f. Maybe also it's good to give you some also some picture or just to use like a graph of function and just somehow visualize the transformation which we have here. Let's assume that the function f, it is equal to, for instance, do not know. A little bit. By the way, I also would like to note that when you take lambda is equal to 0, the function, the cumulant generating function will be equal to 0 as well, because here you will have exponent of 0, which gives you 1, expectation of 1 is equal to 1, and logarithm of 1 is equal to 0. Therefore, also it makes sense to draw the graph which passes through the point 0, 0. Something like, I don't know, maybe like that, okay? You want to have some convex function, and then you take line or linear function yx. Here y is fixed. Y is fixed. And you take function, you take line. That line has the slope y, that is x y. Here is x. For instance, when y is equal to 0, you have the function is parallel. It is exactly the axis x, and then you can change your y, so therefore your line is moving. And you are interested, and then you consider the value yx minus f of x. Then you measure the distance between the line and the curve. And then the maximal distance, line has to be above and curve has to be below. And the maximal distance is exactly the value of Fenhill-Legendre transform at point y. And maybe the maximal distance here should be something like that. And you get that this distance, it is f star of y. That is a function. What is nice about the function here, it is that just some remark that f star is also convex. One can prove that, and also you can consider that as an exercise. And also you can show that if you take a Fenhill-Legendre transform of Fenhill-Legendre transform, you get the function f itself. Also, you need convexity. F has to be convex. Like it is like a Fourier transform in some sense that you have Fourier transform and you have inverse Fourier transform. Here the same, you have transform and you have inverse transform that is the same. And it has also many other good properties. Some of them we will discuss or we will mention here, which we will use for the proof of the lower bound. But before we will talk about the properties, let me go back to the exercise when we have the random variable with Bernoulli distribution. It is exercise 2.9. Before, as before, let Xi has Bernoulli distribution with parameter 1/2. We computed that the cumulant generating function is minus logarithm 2 plus logarithm 1 plus e to the power lambda. And now we are interested we want to find phi star of x. It is given as supremum. You take supremum over all values lambda. And then here you have the linear function x lambda minus phi of lambda. And you know from your analysis course that to find supremum, the function is continuous. We want to have, say, maximum of this function or all local maximums and then choose the maximal one. But anyway, you need to consider the function, you need to compute the derivative, you need to find the stationary points and so on and so forth. I will not go through everything here. I will just shortly tell you what will be the derivative. Let me just denote the function in supremum by g, and you have x here is fixed minus 1 plus e lambda. Then you need to compute the derivative, and here I just copy the derivative. It is x minus e lambda 1 plus e lambda. Note here x fixed. Consider that as function of lambda, and you just need to write is equal to 0. And if in the case if x is between 0 and 1, you can easily solve this equation, and you can get that lambda is equal to logarithm x 1 minus x if x is from 0 and 1. And this point also you can check that it is local it is a local maximum. Is a local maximum. You just need to see how the derivative change its sign. And also using the convexity, so it also must be a global maximum. Therefore, you will get, at least for x that is between 0 and 1, that supremum of lambda x minus phi of lambda, it is equal to, and you need to plug in that lambda into the formula here. Then you will have x multiplied by lambda. I recall that lambda is logarithm x1 minus x. And then you need to plug in that function into the function lambda into the function phi, which is given by like minus logarithm 2 plus logarithm. You will have plus logarithm 2. And then it will be minus logarithm, and let me see, it has to be 1 plus e to the power lambda. It is 1 plus e to the power logarithm gives you just x 1 minus x. And just continue the computations here, which I would like to avoid. You will have logarithm 1 minus x. And you remember from previous lecture, it is exactly the function e of x, which we introduced for p is equal to 1 over 2. Or at least now, without since the proof and any statement or the proof of lower bound and since any statement, you should be very optimistic to get the right result. Because you have a non-trivial example where you precisely computed the limit, and limit was equal to that function. Then we wrote the upper bound, and we obtained something else, right? Because we obtained supremum of linear function minus another function. But after the computations, we came to the same function. If you consider other simple examples, for instance, the example you consider normal distributed random variables, and you compute that this Fenhill-Legendre transform of the Coulomb generating function, you also will see that it will be exactly the limit. So therefore, you should be optimistic just to expect that in general case, you also should have the same result, that the limit has to be described by Fenhill-Legendre transform. And it is exactly the case under some assumptions. And at the end of the lecture, we will not at the end, but actually now we will formulate the statement of the Kramer theorem, and then we will spend some time to prove it. But to obtain the proof, we will also need to prove some technical lemma first, and after that we will go to the proof of the Kramer theorem. Before we will formulate the result, let also write here the list of some properties of Fenhill-Legendre transform of the Coulomb generating function, which later will be useful for us. An exercise. And this I also left for you. Suppose that phi star is the Fenhill-Legendre transform of the Coulomb generating function. Function phi of random variable xi with expectation xi is equal to mu. Show that. And here there is no, I would say almost no probability anymore. It is like just analysis. You need to use analysis, some limit theorems, and so on to be able to show the following properties. First of all, the function is negative, is not negative for every x from R. The second is that phi star of mu is equal to 0. The next property is that phi star of increases on mu plus infinity and decreases on before mu minus infinity mu. Next, phi star of x is positive for every x that is not mu. And then also show that this file shows that phi star is strictly increasing is strictly increasing on that set for every on the set x, so that mu Of course, Fenhill-Legendre transform can be also plus infinity. And if it's somewhere it is equal to plus infinity, it cannot be strictly increasing anymore. Therefore, we just must put this additional set that or assumption that increasing on that set where phi star is finite and is strictly decreasing on the set x less or equal than mu, such that phi star of x is less than infinity. So actually, what we have that when we consider the graph of function, and then when we consider the point mu, then the graph of phi star, it looks like that. It has to be decreasing here, and then it must not be the parabola. It is something like that. Now we are ready to formulate the Kramer theorem. Is 2.3 Kramer's theorem. 2.13 Kramer. Let C1, C2, and so on be IID, dependent identically distributed random variables with expectation C1 is equal to mu, that is a finite number. And cumulant generating function phi of lambda is equal to logarithm expectation e to the power lambda c. Or lambda from r. Here I recall that infinity as values of phi is also allowed. Let Sn be the sum. Then for every x larger or equal than mu, you have that limit of that n goes to infinity, 1 over n, the logarithm, the probability, 1 over n Sn larger or equal than x is equal to minus phi star of x. Where phi star is the Fenhill-Legendre transform of the cumulant generating function phi. By the way, the same result also is true when you will switch this inequality to the less or equal. You take x smaller than mu, and also you will get the same right hand side. But the second result, it follows from this one. Okay, now before we prove, let's prove some technical lemma. 2.14. Then assume that phi is a cumulant generating function associated with the random variable xi. Assume let phi be the cumulant generating function associated with xi. And let also phi takes values from R. Let phi of lambda belongs to R for every lambda. Then phi is continuously differentiable Here you can also prove that phi is infinitely many differentiable, but we don't need that. On R, and phi star of the derivative of phi at 0 is equal to the expectation of the random variable xi, and when you take the limit that lambda goes to plus infinity, phi prime of lambda, that is equal to essential supremum of xi. It is like supremum, but you need to remove bad points or bad values of xi, which appears with probability 0. Actually, it is the intuition. It is not strong definition of essential supremum, but I hope you remember what it is from, for instance, from your analysis course or function analysis or measure theory. It is the essential supremum or again, you can think about, if you do not know what that is, you just can think that about about the supreme. It is not exactly true, but it is. Okay, now we want to prove, and here we have to prove three claims. One claim that phi is continuously differentiable. The second, that derivative at 0 is the expectation. And also we need to compute the limit. And to prove differentiability of the function phi and the continuity of its derivatives, you can use just the definition of the limit and the dominated convergence theorem to exchange the expectation and limit. Therefore, you can get the continuity almost for free, but of course you need to take into account that the function takes values from R. Here I just would like to compute what the derivative is, in particular in 0. Let me also specify what I mean that you need to use the dominated convergence theorem. Recall that the function phi, it is the logarithm of expectation. And you care about differentiability of phi. And for that, you need only the differentiability of the expectation, because logarithm is differentiable function, and you can use the differentiability of composition of two functions. And you need to focus on the derivative of expectation of e lambda x. And here you need to write this derivative as a limit. You know that expectation exists for every lambda. You need to use the dominated convergence theorem just a little bit carefully, and then you will get that you can exchange the expectation and the limit or the derivative. Oops, I'm sorry, here should be xi. And then you will get the result that limit exists, and it is equal to xi e lambda xi. And then also you need to use, again, dominated convergence theorem to show the continuity. Therefore, you have that the derivative of the function itself, it is logarithm. Therefore, you will need to compute the derivative of logarithm first, and it is 1 over, and I write that. And then you multiply by derivative of the expectation, but we computed it the line before. For every lambda from R. You see that if the taking lambda is equal to 0, you get, I want to write that here, lambda strich at 0 is equal to, and lambda taking 0, exponent to the power 0, it is 1. You will have expectation xi divided by expectation 1. It is expectation xi. Well, therefore, we already proved two parts or two claims in this lemma. And the last, we need to compute the limit as lambda goes to infinity, and we will also use that formula to make the conclusion that this converge to the essential supremum or supremum of the random variable Xi. Let me denote the essential supremum by beta. It is supremum of Xi. And also here in this proof, we will cheat a little bit. We will assume that it is finite. If it is infinity, I will leave that for you as an exercise, and just you need to repeat some my arguments to also make conclusion that the lemma is true in that case. But here we consider essential supreme the case when essential supremum is finite. And also, we will consider two cases. The first case, let's assume that actually Xi takes value, this maximal value, with positive probability. This case is much simpler, and here it will show you the reason why you should expect or why you should get this statement, this equality here, through the direct computations. And when this is not the case, still the idea or this reason will remain the same, but you will need to do a little bit additional technical work to come to that result. So therefore, it is always makes sense to consider the simplest case where you can do something precisely, and then try to understand how you can do that in a more general case. It is exactly what we want to do in this proof. We assume that probability is positive. Then the limit that lambda goes to plus infinity, p prime of lambda is equal to limit lambda goes to plus infinity, the expectation of Xi e lambda Xi, that we just take that formula from the computations before. It is equal to, and now let's divide and multiply and divide by e to the power minus lambda beta. You will have here e minus lambda beta divided by e minus lambda beta, and then you have the expectation. Why I do that? Let me first tell you, and then I will continue. You see that when you send lambda to infinity, actually the problem here is that you have this term goes to infinity. And if Xi takes positive values, this also exponent goes to infinity. And you have infinity here. And when you also consider this part, also that goes to infinity. And you have infinity divided by infinity. And you need to do something. Therefore, our idea is to try to remove a little bit here just to make this exponent not going to infinity. And it is exactly what I do here. I just multiply and divide by e, and then I will move this exponent inside the expectations. And we come to the expectation, see, e to the power lambda, and then you minus lambda, and then you have beta minus Xi divided by expectation of of e minus lambda beta minus Xi. And this expression here, it is much better than we started with. And the reason here is because when you consider the limit of the exponent, when lambda goes to plus infinity, you will see two possibilities. Either beta minus Xi is strictly larger than beta. You remember that beta, it is the the possible maximal value. We take essential supremum, but after that we compute the expectation. Therefore, some values of Xi which is taken with probability 0, it doesn't play any role, and you can remove them. So therefore, you can think about beta as a supremum of Xi. And then you have two possibilities. Either beta is strict or Xi for given omega is strictly smaller than beta, then you have that beta minus Xi is positive, and then e to the power minus lambda some positive, it goes to 0 because you have exponent to the power which goes to minus infinity. It will go to 0 when Xi is less than 0. But, oh, I'm sorry, not 0, but beta. And if Xi is equal to beta, then you multiply lambda by 0. And then nothing happens with this exponent. You will have 1 is equal to beta. Then, but this function here, it is the indicator function that, that Xi is equal to beta. Then using the dominated convergence theorem here, you can or probably even you can use here monotone convergence theorem, you can come to the result that you have the expectation of Xi indicator Xi is equal to beta divided by expectation Xi is equal to beta. And now you see why the fact that Xi is equal to beta with positive probability plays a role here. Because in that case, your denominator is not equal to 0. And you can, oh, that is not 0. You can remove this beta, you multiply Xi by indicator, therefore Xi is equal to beta. You can replace Xi by beta, nothing happens. You can move beta outside the expectation, and you have two the same expectations, which cancel each other. And the answer here will be, the limit will be beta. And the problem is only when the expectation in the denominator is equal to 0. Because formally you can write everything, but that you will come to the result that you have 0 divided by 0, and you cannot push this idea further. And then you need to be in the case that p Xi is equal to beta is equal to 0, you need to be a little bit more careful and maybe clever, just to a little bit correct the idea which was presented before to come to the same result. And let's do that. Let me let's consider some beta tilde. So and here the idea is, okay, we cannot work with beta, but then we can go a little bit below of beta, and then maybe everything will be good. So let's consider let beta tilde be smaller than beta. So then you have that the probability that Xi is larger than beta tilde is positive. So it is by definition of beta, because the beta is essential supreme. In that case, we can estimate, we can do the same what we did before. We consider limit and here to plus infinity, but let me write the lower limit first. So here the problem is that so here you see that everything was nice and we could start from limit, and you see that at the end the limit exists. Here we want to write some estimates. Therefore, I start from the limit below and I consider that. And then also we multiply and divide by e to the power minus lambda beta tilde, and you can come to limit. You have that the expectation, see, e to the power minus lambda beta tilde minus xi divided by the expectation e minus lambda beta tilde minus xi. And now I want to remark that note that the limit when lambda goes to plus infinity, the expectation of xi, the indicator that xi is less than beta tilde, e minus lambda beta tilde. Actually, I consider the expression which was which was above. But I multiply only, I see what happens, what is the probability when xi is strictly larger, smaller than beta tilde. And I divide by the expectation that e minus lambda beta tilde minus xi. And then let's note that the limit here is equal to 0. And here the reason is the following. When we consider the expectation in the numerator, or maybe not expectation, but the function itself, minus xi, it goes to, you see that if that doesn't happen, then indicator gives 0, and you will obtain 0 for xi larger or equal than beta tilde. But if it happens, then you see that you multiply you have here some positive number for fixed omega. And when you send lambda to plus infinity, you will have e to the power minus infinity, which gives you 0. Which gives you 0 as well. Therefore, the limit is equal to 0. Also, I want to note that this expectation is finite. When lambda goes to plus infinity, it decreases to 0 because exponent is monotone function. Then the numerator goes to 0. And the denominator, here you can split on two cases. You can write that as the expectation, and you will have e to that power multiplied by that xi is less or equal than beta tilde, plus indicator that xi is larger than beta tilde. And the second indicator is not 0 with positive probability because of that property, which is here. Therefore, you see that here in this expectation, there is a part which goes to plus infinity. And this goes to plus infinity. And this explains why the limit is equal to 0. And it is good because now I have this term, when I put inside that the indicator that xi is smaller than beta tilde gives me 0. Therefore, I can actually remove this part from this term here, and I can continue my computations as follows. It is equal to lim lambda to plus infinity, the expectation, and it is xi, indicator. Now that beta tilde is larger or equal than xi, and e minus lambda beta tilde minus xi. Because with indicator that's strictly smaller, that part is equal to 0. I can split, and one of the term is equal to 0. I hope it is clear. It is written like that. Oops, I wrote equal, but just it has to be, if I'm not mistaken, I wrote that. So here we had we had, no, everything good. It was equal to, it is equal to, okay. And now we obtain that, we obtain just using the fact that C is smaller than beta. Here C must be, I'm sorry, C larger or equal than beta. It is what I had to write, right? I have to write the opposite to this indicator, and it is C larger or equal than beta. But now we can estimate from below, because you can replace Xi by beta tilde, and then everything you can remove. You see that you multiply it here by indicator, therefore you just consider omegas for which Xi is larger or equal than beta tilde, then you put something smaller that you put beta tilde. Beta tilde E minus lambda beta tilde minus Xi divided by the expectation of E minus lambda minus Xi. And you have that it is equal to, here I want to put that beta tilde outside. Lambda goes to plus infinity. And I have the expectation of indicator Xi larger or equal than beta tilde E minus lambda beta tilde minus Xi divided by the expectation of E minus lambda beta tilde minus Xi. And so let's note that the expectation of indicator that Xi is less than beta tilde E to the power minus lambda beta tilde minus Xi, and here divided by the term, it goes to 0. It is what was written here. You just need to also take into account, so just the same explanation, but now as here, but now you need to remove Xi. And when you remove it, you will see that you will see the same, and you can apply the same argument to see that this limit without Xi it also goes to 0. When you put here indicator, then the same reason as before, when we remove one indicator, we can add that indicator. And it tells me that I can just adding this additional indicator to, I can remove the expectation. Let me write this precisely. It is equal to, I want to copy that part. And go to another page. And then you can write here plus beta tilde limit lambda goes to plus infinity expectation and then indicator. And then this limit, as we said, it is equal to 0. Then we can put two limits together. And when we do that, then you will have sum of indicators, which is equal to 1. And it is what I want to obtain. Beta limit lambda goes to plus infinity expectation of E minus lambda beta tilde minus Xi divided by expectation minus lambda beta tilde minus Xi. And this is equal to 1. And that is for every beta tilde smaller than beta. And now we may make beta tilde going to beta. And we obtain that the limit from below of the derivative, and lambda goes to plus infinity from below, phi prime of lambda is larger or equal than limit of beta tilde, and that is beta. And how we showed the lower limit, And then the upper limit P prime of lambda, it follows just from the definition of beta, because when you write the expression for the derivative, there was xi, lambda xi, divided by the expectation of lambda xi. Then you see that this expectation, that xi you can estimate by beta. You will have beta in this xi, you can estimate by beta because beta is essential supreme. And then you can estimate the limit itself by, I will remove beta, I will move beta outside of the expectation, and you have lambda xi divided by expectation of lambda xi. That is equal to, and it gives that lambda to plus infinity, p prime of lambda is equal to beta. And that was done for the case when beta is equal to r. The general case when beta is equal to plus infinity is similar. You need to use the same argument as here, but now you just need to take beta tilde, and then you need to send beta tilde to plus infinity, and also you need to go through that argument carefully to check whether everything will. Now it remains only to prove the Kramer theorem. And we will prove the Kramer theorem next time, also assuming that the cumulant generating function is take finite values. For infinite values, the proof is a little bit more technical, and then I would recommend you to find the proof in one of the books that I recommend, or probably you found already, about the large deviations to see the full picture of how that result can be proved. After we will prove the theorem, we will go to the case when random variables take values in RD. We will go to the case of independent random vectors. And then we will try to understand what would be the reasonable notion for this expression which we have here. Because here we can, these objects are real valued objects, and you can compare them with some fixed constants which are either larger or expectation or smaller and expectation and so on. But if you are in the case of RD, then from here it is not directly clear what you should consider and actually which kind of result you should get at the end in the right hand side. Therefore, our goal will be just to consider one simple example, try to understand what we can obtain, and after that we will go to the formulation of the large deviation principle. That also, I hope it will be done next time. And it is everything for today. Thank you so much for your attention.